Happy morning, children. Welcome back to the class. So we are dealing with similar triangles. Yesterday we have seen what is the difference between similarity and congruency, right? And we were able to identify what are the similar figures, and you also gave excellent examples for similar figures and non-similar figures, right? So based on that concept, we're going to move into a very important theorem called Basic Proportionality Theorem. Okay, very important theorem. Before we move into this theorem, we need to have a clear understanding about similarity, especially in triangles. Okay, in general we know similarity means it will have same shape but it will differ in size, right? When it comes to triangle, what is similarity and how we will tell it is similar? So I'll take this example to you. I'll take triangle ABC. When a light falls on the triangle ABC, consider that as a sheet or something. When the light falls on that triangle, definitely its shadow will be formed. Am I right? I'm just going to mark that shadow's vertices as A dash, B dash and C dash. Okay. Now can you tell me this a shadow triangle is similar to the original triangle? Obviously, this original triangle only it gets increased and become a big triangle, right? This only is remodified or increased in its size in some proportion, and that shadow is being formed. I mean, so I can call this shadow triangle is similar to the original triangle. Okay, so as we have discussed, we have to denote the similarity with a symbol called tilde. So I can denote these triangles are similar, like triangle ABC is similar to triangle A dash, B dash, C dash. Okay, so this is similar. If any two triangles are similar, what and all will be equal or what and all will be equivalent? All that let's see. If any two triangles are similar, the vertices, if I take here, the vertices A will be equivalent to the vertices A dash. They are corresponding vertices. Similarly, B and B dash are corresponding vertices. C and C dash are corresponding vertices. When it comes to angle, this original triangles, all corresponding angles will be equal. So here angle A will be equal to angle A dash. Though the size gets increases, there won't be any change in its angles. That's the speciality of similarity in triangles. If all the three angles are same, in similarity the triangles will have the same angles though it differ in size. So angle A is equal to A dash, angle B is equal to angle B dash, and angle C equal to angle C dash. And about side, this is the interesting thing in similarity. If I take the sides ratio, that is AB's corresponding side here is A dash B dash. This AB divided by A dash B dash, if I find the ratio to this side, I will get a constant number. Am I right? So AB by A dash B dash, if I find the ratio, I will get a constant number. Similarly, if I find out the ratio between all the corresponding sides, I will get I will get a constant number. That is AB with A dash B dash, BC with the B dash C dash, and similarly AC with A dash C dash. If I find the ratios of all the corresponding sides, I can see that the ratio is a constant number and all the ratios are same, equal. That is the speciality of similarity, and that is a condition for any triangle to be similar. The ratio between the corresponding sides are equal. It will be in some proportion. That's it. That is what is similarity in triangle. The corresponding sides will be proportional. Okay. So based on that, we'll be having some conclusions. This we have seen already. Two polygons of the same number of sides are said to be similar. When we will say that any polygon is said to be similar, not just by looking at the figure, there are some conditions for it. One is all the corresponding angles should be equal. All the corresponding angles of this polygon should be equal to all the corresponding angles of the another polygon. If I have angles are equal, then I can say it is similar. These two conditions should be satisfied. Okay, all the corresponding angles should be equal and all the corresponding sides are in the same ratio or proportional. That is, the ratio between the corresponding sides should be equal. If these two conditions are satisfied for any polygon, then we can say that the polygons are similar. What are the conditions? all the corresponding angles must be equal and all the corresponding sides should be in a common ratio. The ratio should be equal. So these are the two conditions we need to remember. So if I take a triangle like this similar, how I should mention the similarity? Corresponding angles. Okay. So here y, x, z, all the angles are equal. So how I should denote the sides? Similarly here x, y, z, everything is the same. All the three angles of this three triangle are the same, okay, equal. So how I should write the similarity ratio? Same ratio. What is the corresponding sides? Can you identify? Here A, here it is D. Similarly A divided by D. Similarly B divided by E and C divided by F. Okay, all these corresponding sides will have a common ratio. Similarly, you can compare this first triangle with second triangle also. You will get the common ratio. A by P, B by Q and C by R. Everything will have a common ratio if it is a similar triangle. You got it? So like another example, if I have a triangle like this with sides 6, 8 and 10 units and 12, 20 and 16 units. If I say these two are similar triangle, if I see the corresponding sides, so we'll take this itself as a corresponding side. Okay, so 12 by 6, 20 by 10 and 16 by 8, everything will be 2. So the ratio between these two triangles with the corresponding sides are 2. So I can say that these two triangles are similar. Got it, children? Yes, so similar means all the corresponding angles must be equal and all the corresponding sides should have a common ratio. So just like that, we cannot say that any two triangles are similar. We need to check these conditions and then only we can say it is similar. As how you said in the last class, 32 inches TV, 40 inches TV, like that. You cannot just like that say, since it was a first class I left it. So very good examples you have told, but we have to see the ratio between the corresponding sides. If it is same only, we can say it is similar. If it is not same, it is not similar, though it has equal angles. Okay. So now we need to recall few things to prove the BPT theorem, that is basic proportionality theorem. I think you know this already. Areas of parallelogram and triangle, which is very important topic we have learnt in class 9. Am I right? So if I take any two triangles on the same base and lying in between the same parallels, if I have this condition, then area of those two triangles are equal. Super. So if I have any two triangles with a common base AB and lying in between any two parallel lines, the triangles will be equal in area. Otherwise I can say that the area is half into base into height. So this you need to remember to prove the BPT theorem. Okay, so now let's move on to the theorem. Very important theorem, basic proportionality theorem, or else we'll call that as Thales theorem. Okay children, so shall we see the theorem now? Yes. So theorem 6.1, if a line is drawn to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. I'll take a triangle. In that triangle, if a line is drawn to one side of a triangle to intersect the other side. So somewhere I'll take one side, okay, one line. I'll start from one side and I'll draw a line to intersect the other side. If I draw a line like this, then the other two sides are divided in the same ratio. The other two sides are this, AB and AC. So these two sides are divided in the same ratio. That means what? This ratio AD divided by BD is equal to AE divided by AC. That is what we need to prove. If I draw a line like this parallel to the third side, that one of the sides, okay, that is the condition. I have to draw one line parallelly to the one side of the triangle. If I draw like that, the other two sides will be divided in the same ratio. So that is what we need to prove. So I'll check the triangle ABC where DE is parallel to BC. Okay, D and E are my endpoints of the line what I am drawing. Then what we need to prove? AD divided by DB is equal to AE divided by EC. This is what we need to prove. Okay, this other two sides are divided in the same ratio. That is the meaning of this expression. So now to prove this, I need something in this diagram which is very simple diagram. We have only one triangle and a parallel line. So we cannot apply any concepts what we know already. So I'm going to have one construction, join B and CD. Okay, I'm going to join this B and CD because as we recalled triangles on the same base and between the same parallel, that concept we can use. And draw DM perpendicular to AC. Okay, I'm going to draw one perpendicular line to AC. Okay, AC, AE, anything you can say AC. And draw another line EN perpendicular to AB. Okay, these are the construction we need to have to prove our theorem. So now let's see the proof. I'll take the construction, what we have done. First step, let's try to find out the area of this triangle, the pink colored triangle. Okay, so if I find the area of that, I can just write the area of that triangle in two ways. One with the altitudes. What we have drawn is En and Dm. Okay, if I take En as the altitude, the base will be AD. In that way, I can write one area. Similarly, I can have AE as the base and DM as the height. In that way also I can write the formula. Now first I'll start with EN as the height. Okay. If EN is the height, the base will be AD. So area of this triangle is equal to half into base into height. I'm taking AD as the base now. So its corresponding height will be EN. So area of this triangle we are concluding it as half into AD into EN. Have that as equation 1. Okay. After that you come to this triangle BD. In that triangle BDE, find out the area, again half into base into height. If I'm going to take this BD as a base because this EN will act as a height for this complete side, okay, AB. EN is perpendicular to AB fully. So the same line EN will be perpendicular to BD also. So for this triangle also the altitude is EN only. So area of triangle BD is equal to half into BD into the height is EN. This is your equation 2. Now what I am going to do with this area is divide one by the other. Okay, divide 1 and 2 because it is something related to ratio. So we need to have that ratio 1 by the other. So we are doing the division operation. So I am going to divide ADE divided by BDE area. Just put all the values here. Half will get cancelled, EN will get cancelled. So area of ADE is equal to divided by area of BD is equal to AD by DB. Similarly, do the same process what I told for the other altitude. I'm going to take the second part of this theorem. Triangle area of triangle ADE I can write with this base also with the altitude DM. So half into AE into DM. That is your next equation. Similarly, this obtuse angle triangle, you take this DEC, again half into base into height. For this DEC also, this DM will act as the height. Obtuse angle triangle will have the altitude outside the triangle. Okay, remember. So for this, half into EC is the base and DM is the height. Again do the same process, divide one by the other. So ADE area divided by DEC area is equal to, all will get cancelled, DM will get cancelled, AE by C. Now the recall thing what we have studied in 9th standard, you have to remember. In this triangle BD, just look at this triangle BDE and triangle DEC. Are they in the same base DE? And of course they are lying in between the same parallel. So this triangle area and this triangle area are the same. Very good. So since it's the same, BDE and DEC area are the same, can I replace one by the other? Exactly. So if I write DEC as BDE, this LHS and this LHS will become same. So since LHS are same, I can write the RHS are equal. So as per the theorem, since the triangles are on the same base and between the same parallels, area of BDE and DEC are equal. Therefore, the LHS will become equal. So the RHS will be obviously equal. Hence, proved. I got it, children? So this is very important theorem in this chapter. Very important. So go through this theorem twice and write once on your own. Okay. So with this, we are coming up to the end of this class. Thank you so much, children.